Thank you for the introduction. Can everybody hear me? Okay, great. So I'm here today as a representative of the whole team at IPA and also the Brace Consortium that did the work I present today. So thanks also go to the other guys here on the slides that did a lot of work on the details I'm going to talk about in a second. So my talk is after the great talk for ROS control we just saw. My talk is a little bit more from the application specific application point of view, but yeah, I also want to highlight some technical details of our implementation of a dual ARM manufacturing scenario. So the outline of my talk is what you see here. So first I want to introduce you a little bit about the Brace project, which is a European project where all this work has been done. Also about the different application-specific details. And then actually I want to cover three main things in my talk. The first thing is actually to get the ABB dual arm concept robot, which we use in the scenario, to get that running to ROS. The second thing is I want to go into some details of using Bubeck in such an industrial dual arm scenario. And the third thing, which is one of the main focus points in the Brace project, is to implement a rapid application development infrastructure. And in the end, of course, I will summarize everything. So, yeah, what is Brace? Brace is a European project, and the main aim of Brace is to develop a dual-arm assistant robot for factory workers. So basically, we focused on small batch assembly processes. So for example, if you have scale-up processes, then you usually have small batch size, and their automation is usually quite difficult and specifically difficult from an economic point of view. And then also the concept was that the robot should be there in the factory, and actually factory workers on the floor should utilize the robot. You don't want to have a robot engineer all the time around. Actually, the factory workers should be capable of using the robot. So these are the main goals of the project, and the project is a European project, and it's part of the Factory of the Future initiative in the European Union, which is more application specific, not that much research specific. And we have partners. Bosch was a partner that also introduced a lot of the use cases. The DTI is a Danish Applied Research Institute. Then we had ABB as a partner, which supplied the great robot we could use. Lund University did great work on real-time controllers with this robot, especially force control. You will see this later in the video. And Magellium is a French company, a small company, which is really into perception technologies with cameras, and they did great work on the tracking. And ourselves, we basically were focusing on the system integration of everything and get the system running basically. What you see here in the picture is a product from Bosch, which they actually use internally in Germany in their factory sites, and it's also an assistant robot, which I think is a fan manipulator, and with a mobile base, but this base is passive, so you have to move it around yourself, and tactile skin for safety issues, and to cover that. And so that is already using, but what they basically have is that performance is really an issue there. So they actually, if they put it into this system to production, they can teach it, but then usually the performance is much, much worse than a human doing the same thing. And so they have certain use cases, but a lot of use cases they were thinking of are not covered yet because of the performance. So what was really important for this dual arm robot setup was actually the performance in the end. Speaking of different scenarios and applications, I want to demonstrate a little bit more what the use case actually is. So actually we went through the Bosch plants and analyzed certain different use cases we could basically utilize the robot in. And one use case is actually in one of the largest factories from Bosch in Feuerbach, that's in Stuttgart, where they have different coating processes. And so what you actually have to do, usually they have these needles. What you see here is my fingers, so these needles are quite small. For example, this one is really tiny, and these come in plastic boxes to the factory, and they have to be put into these specific coating trays. So these are trays, and they basically go in the coating process. So actually, what you have to do is you have a box of 100 needles. Take 2 needles, put them in the other tray, and you do that basically all time long. And especially in like these scale-up processes, you get like 100 boxes of a certain type of needles, and then 100 boxes of a different type, and then also the boxes change. So it's really hard for them to automate that. So they actually have factory workers doing this palletizing task all day long. So we thought it would be nicer if basically a worker could teach the robot the type of needles, the type of pellets, and run that for, I don't know, 100 times, and then basically just teach the next robot that this would be a great improvement for the workers there. So so actually that was the representative use case we were going for. So then you probably wonder, what is a robot system, how does it look like if you want to automate such a task? So I want to show you a little bit the demonstrator that was developed in the project. And as I said, it's less research focused, this kind of project, so we try to use standard or at least available hardware when putting together this demonstrator. And beginning on the lower side, we use the Fraunhofer IPA RobotWorks 3 platform. That's what you see here. It's a sibling of the CareRobot, and it's one of our main development platforms at EPA for service robotics and industrial use cases. And basically, this robot is a mobile platform, but it also takes care of the energy management for the open-pool robot. We have quite powerful CPUs here for doing all the processing, and we added a pneumatic tank here. You cannot really see it, but here there's a pneumatic tank for the pneumatic gripper system, and all the electronic setups you have to do for the rest of the hardware. But what is maybe a main message here is that we use ROS for all our robots, also the RobotWorks 3. And therefore we also imposed ROS to the overall system. And what you cannot see here, because that's the version from January this year, is usually we implemented a lifting unit here because in the tests we actually figured that we have different table sizes, and since the workspace is quite small, we added a lifting unit here. Then the main part, at least for speaking for my talk, is the ABB Frida robot. Sometimes I still say Frida because that was the name of the robot when it was developed, but the official name is ABB Dual Arm Concept Robot. So accidentally maybe I sometimes say Frida, sorry for that. And then we have a sensor head where we basically could have an arrangement of different tracking systems. I will go into that in more detail later. And then what is very important for the task in the end is the gripper system, which you see here. And it's a pneumatic gripper which is built up of parts from chunk, but the most important thing is above the gripper is the passive compliant unit. And one of the research goals was also to investigate if you can do these like small part pack and hold task with passive compliance, because passive compliance usually is faster than having an active control and active compliance systems. Okay, so so we have this ABB dual arm concept robot, which is a great robot, but the question is how can you utilize this robot? And First of all, what is great is that in the back, actually this white thing you see here, there's a full-featured ABB controller in this robot. So, so you can actually have a standard ABB panel, and you can use all the ABB motion tasks and things like that, or linear movement motion and so on this robot right out of the box, which is great already. But of course, we also wanted to do path planning and so on, because it's a dual robot, so we wanted to utilize that in ROS. And since it's an ABB controller, the first thing we did is we tried out the ROS Industrial ABB client, which was available back then. And the first thing we figured is, well, it actually works right out of the box. So it's actually like with 1 or 2 days, we had the manipulator running in ROS, which was great. Of course, then you had to do all the UNF setup and things like that, but the main thing was running right from the beginning with a but, of course. So one but was actually that the ABB client is for one arm, actually for industrial ABB robots, so you only have one. So we modified the Rapid script. So Rapid is the language you use on ABB robots if you want to do things on the controller. So we modified the Rapid part of the ROS Industrial client to support more than one arm. And then we actually, that means that we had to basically add an additional simple message connection. Simple message is a protocol that's spoken in ROS Industrial between the ROS side and the controller side. So we had to add a second connection, and then we used basically two of the different ROS Industrial client-side applications for each arm, so left and right. So that basically meant that we only had to modify the Rapid side, and the ROS Industrial client side was completely unmodified, the standard ROS Industrial client. In the beginning, just to say that, which was, I think, sometimes 2012, we still had to modify this slightly to support the 7th degree of freedom of the ABB robot, but that is, from what I know, that's already in the current version that's supported, so you don't have to change that anymore. So great, so we had in a very short time, we had a complete setup running with controlling the Frida robot from inside ROS. The only problem, which actually we figured out later, was that we still had some performance issues. And when we first tried it, sending joint directory actions to the RAM, that we didn't saw that, but when we started using Move It, and the directories were like 100 points or even more long, then we saw that in the original implementation of the ROS Industrial client, each directory point was sent with one by one with each package, and that was a performance issue. Speaking of performance issue, I'm not speaking that like after plan it takes like 2 minutes to download the directory. That's not what I'm saying, but it took like 1 second or something, which was already too long for us. So that's where we started to do some performance improvements in the setup. So we started extending the industrial client and also the Rapid side, of course. So what we did, we added an additional message type. So in simple message, you have different message types, and we added one to actually allow sending the full directory in one package. So yes, that's what we did, and we also had to add it to enlarge the default size of a simple message package for that, because the directories are longer. So we submit the directories at once, and what we saw is that improvement of about factor 10. Sending one directory is about a couple of 100 milliseconds now. And then also another change we did, what have to say, with the setup, with the sending, that's what we actually use till the end of the project. So that's just a small size of the change of the ROS Industrial client. We did another change. I will come back to that back in a second. We also added a message type for commanding Cartesian set points via the ABB ROS Industrial client. Yeah. So here we have the reader running ROS. Actually, what we also wanted to do is wanted to use Bubeck, so I want to go a little bit into detail of how we set up Bubeck to work with the dual arm robot. So what we did is we have basically 3 separate move groups. So move groups are the thing you set up in Bubeck where you basically describe the kinematics of your robot and you basically select a certain kinematic chain for planning the path. And so of course you have 2 kinematic chains for each arm. And then we added a third kinematic chain that consists of all 14 arms, and with that you can actually then use do dual arm movements at the same time if you have a goal for both arms. Actually, in reality, you have much more move groups because I would say you have multiple tools. In our setup, it was a camera in the range of the arm, and then you have the actual end effector, and sometimes, not in this project, but also in other projects, you also have tool exchangers, so you have to also have the exchanger as the end effector. Unfortunately, Bubeck only supports 1 tool per move group, so what you end up with is a lot of move groups for the different end effectors. But so that's maybe also already a result or a summary that it would be great if we, like Bubeck, could support more tools. And I will come to that in a second when I show the videos. So I prepared some videos. I hope you can see it. So the first video is actually the Arbis window with the Bubeck, and we actually plan a trajectory where the arms go in this mode. So I actually have to do dual arm planning, and what you see here is free to actually execute the motion. So very simple motion. The second video actually shows the same motion vice versa, and what you see here is that the planned trajectory is a little bit more complicated. And in the third video you see it's even worse when we do another plan. Okay. Okay. So first thing, what is great, is that it's actually a dual arm motion completely planned and without collisions. So that's a great thing. And also, if you set up Bubeck, you get these results very fast. The bad thing is that the simplification of the trajectories is still a problematic thing, and Benjamin, who did all this development, he invested a lot of time in trying to simplify the trajectories, so the movements are not that funky anymore. But still, in the end, we still have sometimes these large movements, and of course, in the end, it's still a collision-free motion. But in practice, if you have a human worker right on the side of the robots, these motions are actually problematic. So so I hope we can focus on that more after the project. And one result is that actually teaching these multiple arm motions is actually difficult. So you have it takes a lot of time to figure out when to call what action. But I will come back to that in a second. First of all, another thing we had to do is actually we have a lot of Cartesian movements like linear motion in our applications. So another thing is that the ADB robot has quite a lot of joint constraints. So we have joints where you actually have only a small degree of motion you can use. So we actually had to compare different motion planners, and of course we started with KDL. That's what you use when you start to move it. And there it actually works, but you also have a lot of reconfigurations when you do linear motions. We also tried IK fast, but I don't know, we are usually, like when we use the IK, we generate the IK fast plugin, we had the problem that a lot of times certain motions didn't find any solution, so we had to do retries and so on. And the best thing actually is we came up, or we found, is a plugin which is not merged into the main Movit tree yet. It's still a pull request, but we used it. It's the LMA plugin, and it has much better performance compared to the KDL. But still, sometimes you have these large movements due to reconfigurations. So we also tested the ABB controllers, kinematics of course, and we interfaced that with a simple message protocol extension. And there, of course, you have all the features of an industrial IK solution in an industrial controller. So you have the reliability, also the repeatability, which is important. But you lack, of course, the collision checking, which you have automatically move it. So at the end, actually, we used the combination of LMA in Movit and the industrial implementation in the controller. So in one application, we basically switched the IK solvers. The only problem I see here is that this is not really supported in a sense of the infrastructure. So one thing could be that, and I think that's also already discussed, that you have different plugins in Movit for different IK solvers and switch between them automatically, maybe. So coming back to the slide before where I said dual arm motion is fast to develop, we implemented a scheduler. So what you can do with the scheduler is actually like in the application, you send certain commands to each arm in whatever arbitrary order. Then you specify certain points in the application where you have a synchronization, where you basically both arms have to be at a certain position at the same time. And then the scheduler takes care of managing that and calling the right Movit plans or move group actions in there. So I just put an example here. So what you do in the application is say move lin left, PTP left, lin right, PTP right, and so on. And then actually you say execute, which is the synchronization point. And then what it does is it's basically scheduled it into like dual arm planning requests, and then it requests these plans from Movit, and when it gets the result, it also merges the resulting plans into one trajectory, so you can actually utilize the trajectory interpolation of the controller. And oh, the color changed. Yeah, so that's you can find that on GitHub in the Brace controller repository. You also already open source that. And also what it does, it actually, depending on the end effector you comment, it looks up what move group to use. And with that in place, I can show you now a video of a more complex application where we used so what you see here is one of these trays I talked about at the beginning with needles in it. And you see that still you don't have a head, so it's more early video. So, so the first motion is not dual arm, but then we actually use the dual arm motion. And what you also see is that we still didn't have the performance we have in the end. But what you see is basically, so the plans are all planned using Movit, and actually the application was developed that we first developed the movements for one arm, and then for the other arm, and then the scheduler actually automatically merged the two things. And also what you see here, that's just small details, that we had to develop a palletize application where you basically can generate different pallets and so on. And yeah. Okay, so that was just a demonstration of what you can do with such a Movit setup. And in that video, I want to summarize a little bit the challenge we basically faced when using our Movit and the ROS industrial stack. So as I said already, exchangeability of implementation of Cartesian solvers would be great. Also, if usually if you have an industrial manipulator, you have good IK solvers in the robot. So also utilizing that in a ROS environment would be a great thing. Then one thing which actually, so we have a ROS industrial specification of how a ROS industrial manipulation driver has to look. But what we don't have yet is a standardized way of Cartesian interfaces in ROS, so like standard message types for Cartesian motions. So in this project, and I've seen quite some projects at Fraunhofer, we used another specification of how we call Cartesian movements from ROS. So, I mean, most of these messages look the same, but still some small differences are. So maybe that would be a goal for the near future to standardize a little bit on this Cartesian interface, especially from the ROS action side, actually. Then, that's like my colleague also actually said, we should put that in also because MoveIt is great and also great documented, but whenever you run into problems like with this simplification, you can ask questions on mailing list, which is great. You usually get responses, but there's no like real troubleshooting page regarding these issues. So he actually had to look in the source code of MoveIt quite early. So just the feedback that, of course, that's also feedback for us because we could start such a troubleshooting. But yeah, and then one thing I didn't talk about yet is because we have these small needles and these are really small, we have really precise motions. Actually, the calibration between the UADF, what you have on ROS, and where you plan the motions for, and the robot executing has to be very precise. And for that, we didn't find a solution yet. So of course you can do somehow visual calibration, and what we ended up with is actually extracting the calibration of the ABB robot, which is in the controller, and then use that information on the UADF. And usually, from what I know, at least what I from what controllers I saw until now, almost all vendors actually have a calibration in the controller because they do that calibration when they put have the robot gets the robot out of the factory. So actually extracting that in an automatic way would be a great improvement for this precise motions in the ROS community, I think. Okay, so that was a little bit my summary of the first two parts of my talk, where I spoke about the MoveIt and the ROS industrial interfaces. And the second part, or third part actually, I want to speak about rapid application development, because as I said in the beginning, one of the goals was that the factory workers on site actually uses the robot, utilizes the robot. So we developed the concept of something called AUA at the beginning of the project. AUA stands for Assembly Unit Actions. It's just another word for skill or app, whatever. So you have a lot of these names floating around in the ROS community, at least in Europe. AUA is just another one. But what it actually means is that you have a platform-independent part of application that is quite high level, so an end user can actually utilize. And then, of course, every robot system implements such a high-level skill, AUA, whatever, in a specific way, and we call that primitive, at least in Brace. And this AUA, of course, has to have a formal specification how it looks like. So that was a concept. We also, you see in the picture, thought about how a formal description should look like. And then what we did is actually that we developed based on this formal description, we tried to use a model-driven approach. And we, of course, want to separate the different things, coordination and configuration. And as you know, we also use Bright quite a lot at IPA. And so we extended Bright for this project actually, and implemented a lot of the things which we have in Bright right now regarding application development. So that means we call that coordinator development in Bright, but basically it means application development. We extended that quite a lot during the Brace project. And what you have there then is a separation between what the robot developer, the expert sees, which is a primitive, and what an end user later on sees in a GUI that I come to in a second. So the workflow we are aiming at is actually that the robot developer creates an AUA, which is actually a state machine, a smash state machine, which you create using Bright, which is, you cannot really see it, but looks like that in the right corner here. And basically you implement the state machine, and then what you can do in Bright is actually that you take the state machine and just change a parameter and says, okay, this state machine now is in skill on AUA I want to expose to an end user. Then you also select which are part of the configuration, which of course can be quite complex when you have a complex application, which part of the configuration is also supposed to be exposed to an end user because he understands what he can do. And then, based on that small change in the model, the toolchain automatically takes care of that this AUAs appear on the end user screen, end user GUI, so he can actually configure the application then. And of course, it also means that we have to have a solution for fast and easy configuration of these states for the robot developer, but even more important for the end user. So that's where we came up with something called Comp Teacher, and you can guess from the name that it was originally created for the Carobot, but we extended that quite heavily, and what it actually does, it's a small tool. We plan to integrate that into Bright actually, but right now it's still a small Python tool, which actually lies under my GitHub account, so it's a Bubeck/CompTeacher. But what it does actually, it passes a YAML file, and in this YAML file, basically you have all the entries from a ROS message. So what Bright actually does is for each state, it generates a YAML file, and in this YAML file you have the configuration for the execution of that state, which is basically just, for example, if you call a follow join directory action, it will halt the actually directory action it will use. So in the end, it is a ROS message entry, and it passes that, and then visualizes the fields of that ROS message entry onto a GUI. So, well, okay, that's not really fancy, but what it then allows you is that for certain common ROS message types, like for example a post stamped, you can actually implement teacher plugins. So you can implement plugins to get the values of a post stamp, for example. And then actually based on that setup, we implemented different plugins for example, the teach in handle, which I'll show you in a second, or also like for example touch up, so you can move the arm and then just take the current, for example, Cartesian pose as input for the teacher, or you can use perception setups. And I want to also show you a view of that. So what you see in the beginning is actually a screen, and what you see now in a second is actually a comp teacher, and I pause that. So actually we have a message type, and then here you see the different entries of the message type, and here it's just the float value, so you just can put in any value. Here's just a string, so you can put in any string. But up here you basically have a goal pose, which is of type post stamp. And what you see now is that when you put down that menu, you see all the active teacher plugins we have for post stamp right now. So we have something here for post input is actually just an input thing, but we have a touch up for the arm, and what actually my colleague selects now is a cam post teacher, which actually takes the output of a camera. So he just puts in that he wants to have the result on base link, then he say teach left. So then he takes the APB arm. What you see here is in the end there is a camera system here and tool cameras, and he just presses the passive compliance unit, and then the robot basically detects the needle. For assurance, it just like points at the needle, and when we go back to the screen, what we see is that we actually have the values here now taught basically based on that teacher plugin. And yeah, based on that, like I said, we have different plugins, so we can actually use that as an input. And at least we think that this is also a way of that the end user can actually teach things like a 6D post. So as I said, we also have a plugin for tracking. So one of the concepts is that the worker uses a teach-in handle, that like a thing that looks like the end effector but can moved by the worker. And so what we have to have is a tracking system for this handle. And we did experiments with actually 3 solutions. So one was a commercial system that was developed by Magellium, the project, which really focused on low cost. So we can use actually any monocular camera, webcam, whatever, to do this tracking. And you see that here in the left image. So these are actually colored. You cannot see that quite good, but these are like red, green, and so on, and are actively lit up by LEDs. And based on that configuration, you can actually track 3D track these or 6D track actually these positions of these balls. And another system uses a TIY, it's Teach It Yourself. It's an open source project. You can find that on Google Code. And here you have an IR stereo system. You can also use this setup by yourself. The precision of the system is much better than the low-cost system, of course. But in the end, we had to be honest. In the factory test, we used the commercial system for OptiTrack because the others had problems with color T-shirts and things like that, also lightning. So we had to, for the factory test, we basically said we use a commercial system which was more stable. Okay. So that's just a small screenshot. So in the end, the AUAs you develop show up in this web GUI. The sense is similar to something Brian showed me, I don't know, 3 years ago, which was an Android GUI for the Peer 2. In the sense it's similar, but I think that was not continued developed, right? I don't know. But so it's a web GUI which you can use on a cell phone or browser, whatever. And here on the left side, the different AUAs that are supported by the robot show up, and you can actually add them to an application, which is that on the right, and then use the ComTeacher mechanisms like the teach-in plugin to actually teach the different configurations, and then just press play and execute that. And that's what we actually gave the workers in the factories in the end. So. In the end now, I think I have still some minutes. I'm just going to show you videos of the different applications we had in the factory test. So that is a video. So here we use just the navigation to go there. Then we teach the poses. And then the robot actually is starting the palletizing application. What you also see now is that we use the motion controllers from Lund to actually solve the pack and hold problem, because as you saw, he taught the position, then the platform moved, so actually the position that was taught in the end was not very precise. So we had to basically have that tactile motion to actually put in the needle. The great thing about that is that it's really flexible. The bad thing is that, of course, it takes some time to put the needle in, so the performance was not that good. Then you see the same thing by touch up. So he activated the teacher, then he actually puts the robot into the different parts. What you see is that he sometimes puts the hand on the end effectors, and he usually pushes the gripper, and that's here you see another strategy of solving this pack and hold problem which we developed, which actually utilizes the passive compliance of the end effector quite good. So and that's also really fast. So that's real time. And I think now we speed up in a second. So yeah, so that's 5 times. But what we want is to show you is that we actually completely empties the tray. And then the end, the last thing I can show you is so another way of finding out where the tray is actually is this tactile teaching. So actually we basically set up different degrees of freedom, like the height of the table or the X, Y, and rotation of the tray, and actually then by tactile feedback it actually taught the position of the tray. So it's actually the only thing the worker then had to do is take the handle and then basically point at the middle of the tray. And then, as you see, we again have this this motion of putting in the needle. Okay, so to summarize, what we did is that we used the ROS industrial drivers with this dual arm concept robot, and hopefully it will come out soon. So all of you also can use, and the concept is gone off this name. Because it is actually a great robot. And then we used MoveIt for precise and fast, should also say, dual arm motion planning. So, we implemented such a rapid application development process. So the outlook is that we currently are in the process, so the end of the project is near, it's in about a month. So we're currently revising the software, and I hope that we can open source. Most of it is already open source, but I hope we can open source the rest too and open source as much as we can. The demonstrator I showed you will continue to be used by Bosch and also by IPA in Stuttgart for other research projects which are planned. And also this rapid development process turned out to be really great also for other applications, so we'll use that. So the web page is that. It's a little bit empty, but it will fill out soon, I guess. At this point, I also want to thank also the team at IPA, also all the partners in the project, and the European Union for funding such a project. And unfortunately, I think we don't have so much time for questions, but if you have, maybe, I'm open for questions.
Motion-based battery power. What kind of processor did you have? How much power did it require? How much power did the ABB controller consume versus your PC boards? How long could it operate?
So So the question was about how long or in what way the robot can basically run without any power supply or other supplies. So what you see here in the system is a battery down here. So it's a battery pack. And with this battery pack, we can run the whole robot of about 2 hours, something like that. And actually, the power consumption of the ABB robot is quite low because it's for very small parts and light parts, and so the motors in the robot are not very big. And then additionally, we had a pneumatic tank, and here it depends. So we had sometimes we had some leaks in the vents or something, and then you don't go really long. But in theory, it depends on your system. But usually you don't need a lot of air for this small grippers. So I would say, I mean, this is still a research robot. So we also have a robot working, for example, 2 battery packs, so you can extend that. What kind
of processor was in there?
Oh yeah, sorry, I forgot. Yeah, you also asked about the processor. So in here we can put in up to 3 CPU boards. In this system we used 2, which are 2 i7 boards. So we didn't really focus on embedded, but with 2 i7 boards everything was fine, also the processing, for example.
Yeah, I was wondering, could you talk a little bit more about maybe the IK solvers and the fact that you actually use a mixture of them? Like, what did you use from ABB? What did you use from?
Yeah, so for example, in So in the motions, the video where you basically go from this pose to that pose, we used actually the Bubeck sole because that was important that we have position-free things, especially because we also use both arms at the same time. Of course, in theory that shouldn't be a problem, but in practice it sometimes is, depending on the configuration. But for example, in the peg and hole movements, there we use the ABB controllers because there it's really crucial that you don't have a reconfiguration right when you want to put in the needle. So so that's why we basically came up with that mixture.
All right. Thanks, Alex.
Okay.